Okay, so today we'll talk about gravitational wave detection. And I don't mean to explain like how does the interferometer work or something like that. Let's bring an experimentalist, a true experimentalist for this. I'm gonna explain the part where you take some data, okay? And you somehow see that maybe that thing is the gravitational wave you are looking for, okay? So we'll get data to detection. And this is it will have three parts. The first part will be mostly theory. Next, we'll talk how is it actually happening in practice. And maybe later we will talk about consistency tests, which is something a little bit detailed, but I think it's worth to know. Okay, so without further ado, I want to first make a short survey. Who here knows who have learned statistics? Raise your hands. Who have learned about the Nyman-Pearson lemma? Okay. Who have heard the words matched filter and know what they mean? Okay, so most people know matched filter, but they don't know Nyman-Pearson. To me, this is like, you know the wave equation, but you don't know the Maxwell equations. Okay, so let's go step by step and build everything, and we will see that it is actually useful later. Okay. So first of all, in statistics, and there's probability. And the connection between these guys is very similar to the connection between physics and math. Okay, so what do I mean by that? What I mean is that once you have set up the question, once you have set up the model of reality, then all there is math. But that doesn't mean that the field of physics doesn't exist. It just means that the entire complexity is in the framing of the question. And that's true also for statistics. Okay, so the art of making statistics, just like the art of making physics, is to choose an approximation of reality. It's not correct. It's just an approximation of reality that is good enough to be A, solvable, and B, predictive. Okay, and we will talk about the approximations that we found useful in gravitational wave data analysis. Okay. So without further ado, let's talk about a statistical test. So first of all, before a test, a hypothesis. Hypothesis is a complicated name, but it's actually, it has only one feature, okay? You see data, okay? And this hypothesis, it's some function of the data, okay? That it's supposed to be the probability density of seeing this data, okay? Probability density. So why do we have so many words in statistics to concepts that are all the same? It's because, but when we say hypothesis, we mean a probability distribution with the intention of saying, I don't know if it's correct, not correct. It's a hypothesis. Okay, so it's more like an English definition than a math definition. The math definition is that it's a probability density. Okay. Now, a simple hypothesis. Okay, so a hypothesis, as I've defined, maybe has some parameters. Okay, so you might say, if I know theta, then I know d. Teja wrote it like that: probability of d given theta. Okay. Good. So that's a hypothesis. A simple hypothesis a simple hypothesis is a probability distribution such that there's no theta, okay? No free parameters. Okay, that's a simple hypothesis. This hypothesis that has a theta, it's called the composite hypothesis. Okay? Okay, so why are we talking about this? It's because there's one theorem, one actual theorem in statistics that I think everybody should know, and it's the Neyman-Pearson lemma. Neyman-Pearson lemma. Okay? And it states the following. If H0 and H1 are simple hypotheses, then the most powerful test, and we will define what is the power of a test, most powerful test is probability. So this is a function of the data, okay? Probability of data given H1 divided by the probability of data given H0. And we are comparing it to some threshold eta, okay? Okay, so the test T is to take the data and to compute something, and then we compare it to eta. Now, what is the power of a test? Okay, so every test, if I have a, the option to have H0 and the option to have H1, okay, each one of them, and let's have a cartoon, okay? So let's assume that the data is one-dimensional. You don't need all these assumptions. I just want to plot a cartoon, okay? So probability of data given H0. Okay, so maybe you will have something like that. And I need a different color. Probability of data given H1, maybe something like that. The eta, maybe something like that. This is eta, okay? And we will define the errors, okay? So if we are above eta, we say it is H1, okay? And if we are below eta, we say it is H0. And there's an error term. So this blue area is the probability. So that's by mistake 1, okay? And that's the integral from minus infinity to eta of probability of T of D in smaller than eta, okay, given H1. Okay, and that's the D in some sense. Okay.
But the contrast with each one is kind of low. That's why I would make it better off sticking to white.
Okay, do I need to write this again?
No, it's okay. I know what it says.
Okay.
What's the right part?
What is the right part? It's the integral. We're integrating over something.
Sorry, the red last, yeah, the last term. The last term in red is gonna be.
Okay, so so this is the probability to say by mistake, okay? So by mistake 1, Okay, to say by mistake that the data came from H1. Okay, so sorry, what am I doing? It's H not. This is beta 0. I will always flip them. That's a theorem in statistics. I will always flip them. So it came from H1 actually, right? And our inference was that it's smaller, because it's smaller than eta, I said it is H naught. So by mistake, H naught. Okay, so that's an error term. There's an equivalent error term, which is beta 1, and that's this area. Okay, so that's integral from eta to infinity, okay, of definition. Probability of T of D is larger than eta given H. Okay. Okay, so here is a test, and here are properties of the test. Okay, until now the test was not defined. Okay, but it is defined. But here are properties of a test. Any function T of D, okay, would have some properties. And the power of the test is what is called maybe the 1 minus beta 0. Okay, so the power is 1 minus beta 0. Okay. Yes.
Can I be alone?
Yes.
So I think that you can either erase the integrals and write it as is, or write equal to eta and then do the integral.
Okay, fine. Thank you, Jonathan. Oops. Okay. So the power of the test is this 1 minus beta 0. And we want to compare tests at a given beta 1. Okay, so beta 1 is fixed. I don't know, maybe you asked the dean what is the false alarm. So beta 1 is also called false alarm. So you ask the dean what is the acceptable rate of, retraction of papers, and he says, 1 in a million, and you say, okay, fine. Then beta 1 is 1 in a million, and now I want the most powerful test. Okay, and there's a theorem. Neyman Pearson tells you this is the most powerful test out of all tests, whatever it is, linear, nonlinear, whatever. Okay, that's the most powerful test. And there's a simple proof for it. Yes.
Is eta?
I ask you. It's a threshold yet to be determined. It's usually eta is something that you determine with beta 1. Okay. So now let's have a mental picture in mind. What are tests in general? Okay. So here is beta 0, and here is beta 1. Okay. And a test, so this is 1, this is 1, and this is 0. Okay. A point here is something realizable by a test, maybe realizable by a test. Okay, so this is, I don't look at the data and I say 1. Okay. I will never ever say by mistake 0. It will never happen. Okay. And I will always say by mistake 1. Okay, so that's a non-informative test. I take the data, put it aside, and say 1, like in politics. Okay. Here is another non-informative test. Okay. I take the data, multiply by 0, and say 0. Okay. That's another non-informative test. Equally political acceptable. Here is another non-informative test. I take the data, multiply by 0, and then flip a coin. Okay. here is a non-informative. So all of those are non-informative. By the way, here is a talent. Okay, so whatever it is, you say the other way. Okay, and this is the perfect test. Okay, so this is perfect. So now what Nyman-Pearson is telling you is that if you take this test, probability of D given H1 divided by probability of D given H0, okay, you will have a curve. This curve looks kind of like that. Okay, and it is guaranteed that whatever other test you can conjure with this data, this test is going to be above this Nyman-Pearson. So Nyman-Pearson is the thing that is minimizing this curve. It's called ROC curve, and bad names. Okay. So now I understand what is this test. And now let's talk about how to prove this, because it takes 1 minute and it removes the charm away. Okay. So it's a very short proof. I'm going to do it on this board. Okay. Here is a statistician. Sorry, it's not a statistician, it's a robber. Here is a robber. Okay. And this robber is entered into a room full of coins. Okay. And there are some coins made of gold, some coins made of brass, some coins made of silver, whatever. And each one is different size, and each one is different value. Okay? And somehow this robber just looked at the stock market and he knows the value of each one of these metals. Okay? And this robber has a backpack, and in his backpack, he knows he can carry only 30 kilograms. Okay? And the question is, what's the optimal set of coins that this robber will take out of his backpack, like into his backpack, and leave away? And this is a very easy problem. Oh, by the way, this robber also has scissors, so he can chop a coin. The last coin he can chop. Okay, otherwise it's NP-hard. And okay, so this robber, it's a very easy problem to solve. You take all the coins, and for each coin, you know what is the weight, and you know what is the value, and you sort the coins according to the function value over weight. Okay, so you have a test. Okay, you're testing the coin, and you assign a number, which is value over weight. And if this value over weight is larger than some eta, then you say, I'm going to take this coin. But then you say, how do I know eta? And I say, okay, you have 30 kilograms. You want to take only 30 kilograms. There is some eta for which you will take exactly 30 kilograms. Okay, and the last coin you chop so that it will exactly fit your bag. Okay, wait. I said robber. Maybe it's a statistician. So if this guy is a statistician, and those are events, data equals 0, data equal 1, data equal 2, and they have different value, as in probability that they actually belong to H1, okay? And they have different weight, which is the probability that they belong to H0, okay? So what is it that we need to do? We just need to compute the ratio of probability that they belong to H1 divided by probability that they belong to H0, and see if they are larger than eta, okay? And the last event, so if it's a continuous space, then there's no last event. But if it's a small set, then chopping the coin is just like tossing a coin. Anyway. Okay, good. So we've proved Nyman-Pearson. Okay. If you look at the proof, it has many details, but the essence of it is this. It's this robber trying to maximize the coins in his backpack. Okay. So now that we know Nyman-Pearson, let's do the one example we care about. Okay. And the one example we care about, before we do that, okay, so I didn't say we are doing theory in this particular part. So it means that we are going to have, so the beginning is going to look like a spherical horse in a vacuum. So here is a spherical horse in a vacuum. And by the time we finish the theory plus practice, it will look like a horse and it will have tracks in where it's running. Okay, so that's our spherical horse in a vacuum. So what is the model which is a spherical horse in a vacuum? Okay, so what is the model? So you have a gravitational wave detector, some interferometer, and there's a gravitational wave going into the board and whatever, and we have this H plus, H cross, whatever. Okay, so we have some, for the moment it's just H of t, okay? It will become H plus and H cross by the time of the end of the lecture, but for now it's just H of t and plus N of t. And Teja yesterday showed like the classical model in which N of t distributes as a Gaussian, normal variable, 0, and some covariance C. And moreover, Teja already said that the covariance is a circular matrix. Okay, so actually he said Toplitz's, whatever. So there's this value and it repeats over, and this value repeats over. Okay. So in algebra terms, this is C of n t n t plus tau, which is some, I don't know, the autocorrelation function of tau. Okay. When I say C, I mean covariance. Okay, so we have some covariance matrix and we have the data. And what does Nyman-Pearson is telling us? Okay, so Nyman-Pearson is telling me if I want to see, okay, so let's write explicitly. H naught says that H of t is equal to 0. Okay, that's what H naught is telling us. There's no gravitational wave. What are you talking about? Binary black holes at the edge of the universe? What are you talking? Barak, it's nonsense. And H1 says H of t is some template. Okay? Some template. And I would even say that this template is perfectly known. So you remember, Nyman-Pearson works only if there's no free parameters. So even the distance, everything is known. Okay, there's on the position, distance, everything is known. It's a spherical horse in a vacuum. Okay, everything is known. Now, what is the perfect test? So Nyman-Pearson is telling me probability of D given H1. Okay, so let's write this. It's a hypothesis. So what it promised me only one thing, that it knows how to compute probability. So probability of D given H1 divided by probability of D given H0. This is what we need to compute. Top part, 1 over square root 2 pi C, whatever, and then e to the minus, and here I will have D transpose, sorry, D minus T transpose C minus 1, D minus T, okay? And there's a half somewhere, minus half, let's make a minus half. Okay, so why is this the probability of the data given H1? So
You should explain your notation for the determinant of C,
the determinant of C.
for absolute value C.
Yes. Okay, you said it. It's the determinant of C. And I hope I. What was the question? There was another question? No? Okay, so why is this the likelihood or the probability of the data given H1? So let's look at this equation. If I subtract T, okay, if I subtract T, then I'll remain with N of T. And N of T, it is written exactly what is the probability distribution. So this is N of T, C minus 1 N of T, which is the likelihood of N of T. Okay, probability of D given H naught is just 1 over square root 2 pi C whatever e to the minus half D C minus 1 D. Okay?
Correct, sorry to be not yes. But your determinant symbol has to go outside of 2 pi. It's either 2 pi to the n determinant of C or the determinant of 2 pi C. Sorry.
2 pi.
2 pi to the n times the determinant of C, or alternatively, the determinant of 2 pi C.
The
Put 2 pi
determinant.
inside of C and then take the determinant.
I'm gonna do this. Okay. So, what did I want to say? D transpose. Thank you. Okay, so here is a test, and Nyman Pearson is telling me to equate this larger or smaller than eta. Now, this test is not what Teja was showing. Have you ever seen these exponents? They should not be there. Okay, so let's do another thing. So I have a test, I have a person, and this person is comparing some function, okay, t of d, to eta. And there's another person, the lazy person. And the lazy person says, I don't know how to evaluate this function, but here is a monotone function, okay? And I'm going to say if it's larger or smaller than eta, than f of eta. Wait a minute, it's the same test. Okay, so if f is monotone, okay, so if f is monotone, it's literally the same test. I can compare 10 to 17, and then if I apply a monotone function, let's say square, compare 10 squared to 17 squared, my comparison is still valid. Okay? Okay. So let's apply a monotone function. What do you care? Okay, and the monotone function I will choose is what? A log. Okay. So this thing is sometimes called the likelihood, okay, or log likelihood. And the log of this is now minus, it's a likelihood ratio, sorry, likelihood ratio. And the log of the likelihood ratio, that's something you've heard, right? And the log of the likelihood ratio is minus half d minus t transpose c minus 1 d minus t plus half d transpose c minus 1 d. And now let's open the parentheses because we can. Teja wrote it. Okay. So let's open the parentheses. Now the d c minus 1d will just cancel. So we'll have two terms. We will have t c minus 1d, okay? And we'll have two of that because the matrix C is symmetric, okay? 2 times tc minus 1d, but the minus half tied, okay? And we will have minus half t c minus 1t, okay? And I remind you, we are going to equate this to eta, okay? Now, this is not the original eta, it's eta prime. I could say log eta, or I could just say, I haven't determined eta yet. What do you care what I call eta? Okay, so I'm going to compare this to some threshold. T is known, okay? So adding a constant, it's a monotone transformation, okay? So that's equivalent, totally equivalent. That's totally equivalent to Tc minus 1d larger or smaller than eta. Again, what do you care? Okay, and now I want to make my life even easier, and I would normalize it. I can divide by a constant. Again, what do you care? So I will divide by the square root of d c minus 1d. Square root of, sorry, mistake, t c minus 1t. Okay? Why am I dividing by this weird quanta? It's because if I compute the expectation value of this given h naught, it will be 0. Okay, so let's investigate this test. Okay.
You should put some transpose on the left. You're missing your transpose on the left.
Okay.
Also, they put you start.
Okay. Good. So, what are the properties of this particular test? So first of all, Neyman-Pearson guarantees it's optimal. Okay, I should look no further. Okay. Second of all, it's very easy to understand what are the statistical property. So D is a Gaussian variable. It's a Gaussian variable. Okay, it has some expectation value that we have two different theories about it. And it has a variance. Okay, that variance, covariance. Okay, so it's a Gaussian variable. A linear transformation of a Gaussian variable is a Gaussian variable. Here is a linear transformation. Okay, it's a linear transformation, right? This entire thing, dotting D, it's a linear transformation. So now what are the properties of this new Gaussian? So let's make let's give a name to this test. I don't know, G. Okay, whatever. So the expected value of G, S is better. It's a test, it's a statistic. E of S is 0. What?
Even H.
Thank you. Wow, you just read my mind. E of S given H naught is 0. Okay, so what is E of S given H1? What is E of S given H1? Okay, so in expected value, this thing is this H, which is T. Okay, so I have T C minus 1T divided by square root T C minus. So that's square root T C minus 1T transpose. And what is the variance of S given H naught or H1? This is what? What? So I have a variable that has a covariance, okay, and I do a linear transformation. So the new covariance, okay, so I should say covariance. The new covariance is going to be the linear transformation, and then the covariance of the thing, which is C, and then the transpose of the linear transformation. So that's C minus 1T. here there was a transpose, but C is symmetric because it's a covariance matrix. So that's T transpose C minus 1 T. And I have divided by the square root of this. So so this is a constant, this is a scalar, right? And the law of variance is that if I divide by something, then the variance divides by the square, okay? So I divide by T transpose C minus 1 T. That's 1. Okay? So now we have a fantastic picture and easy to manipulate and remember. Okay? Now this is too high. What will I do? I don't know. Let the stick come. I did manage. I was warned. And okay, so now what do we know? We know that this thing is 1. And we know this distance. Okay, so that's square root T transpose C minus 1 T. Okay. And now it's very easy if I tell you that I got 7. It's very easy to compute what is the beta 1. Okay, so that's an integral of a Gaussian that is 7 standard deviations away from 0. Okay, roughly 1 in a trillion. Okay, so now it's very easy to interpret. LIGO tells me they have detected this binary black hole and they report SNR. So that's the definition of this SNR. So SNR for a planning of the experiment, it's this quantity, okay? It's this distance in units of standard deviations, okay? And when actually there is a particular event in question, then the SNR is exactly how many sigmas this thing was away from 0. So it's the actual value of the test, okay? So now you know how to detect gravitational waves. Do you? The answer is almost. So now we have this spherical horse. And now we have to add more details. And there are many details to add. Let's see what's the order of the number of details according to my notebook. Which detail do I add first? Okay, so we said that Nyman-Pearson apply only to simple hypotheses. But in fact, I don't know what are the parameters of the gravitational waves that are going to come my way. Do you? Nobody knows, right? So let's simplify the scheme. So first of all, there is an amplitude, okay? And this amplitude actually, you can completely ignore. So if I have a model in which d of t is equal to a times t of t, we'll ditch this h notation. In a times t plus some n. And now because a is a free parameter, that's not a simple hypothesis. Okay, I can close my eyes, think about a as a known quantity, and get a test. And my test is going to be T transpose C minus 1. So AT is now a word, okay? AT. And divided by the square root of T transpose C minus 1. Okay. So this is closing my eyes, applying Nyman-Pearson as if A is known. Okay, that's the test I'm gonna get. And this is a times the previous test, right? Because I have a squared over here, a squared over here, but here is a square root. Okay, so it's a of the previous, it's a times the previous test, which is t transpose c minus 1t divided by the square root t. Okay, now I'm asking you a question. Do I need to know a? Because anyway, I'm going to compare this to eta, right? I'm anyway going to compare this to eta. So I don't actually have to know a. I can just forget about this. Okay? Okay? I can forget about the a. The a, I shoved it into the eta. And lo and behold, I have a test. And if I want a given false alarm rate that the dean has dictated, so it's 1 in a trillion or whatever, okay? And I don't need to know a. This thing is called uniformly most powerful. And the joke about this definition is that it applies to only one case, and that's an amplitude variable, okay? So if you want to read about this, there's the Carlin-Rubin theorem that again does very complicated thing, and in the end it's useful only for that case, okay? So even if this function would have been a monotone function of eta, that would have still applied, okay? But general monotone function I haven't seen. I have seen a constant, okay? Good, so that's uniformly most powerful. Nyman-Pearson is uniformly most powerful. But that's still, so the distance of the binary black hole, now I don't have to know, okay? I got a letter from the doctor. You don't have to know the distance of the thing you're looking for. But I also don't know the masses or the spins. Okay, so what will I do now? So now let's simplify this complicated hypothesis. We're going to say, and that's a very important lesson for life, okay? If you have a statistical problem that is not well approximated by your previous trial, you have to change the problem, not change the solution. Okay, you don't need to say, Nyman-Pearson doesn't work. What you need is to change the problem such that the Nyman-Pearson solution would work for you. Okay, so for example, I don't know which black holes are going to come. So let's have a slightly more involved H1. Okay, so H1 has God inside. God plays with his dice and tells you, I'm going to take theta out of the space of all thetas. Okay, whatever. Okay, masses, spins, and whatever. According to a probability distribution, pi of theta. Okay, so that's the first step. You randomize theta according to some prior. Okay, and then you generate the data. And then D distributes T of theta plus N of T. Okay, T of theta T. And that's according to H1. H naught is still the boring zero. Okay, H naught is still D equals N of T. Okay, now does H1 have 3 parameters? Who thinks H1 has 3 parameters? It has no 3 parameters. Okay, so you owe me one thing. You owe me the probability of the data given H1. So what is the probability of the data given H1? Probability of data given H1 is what? Integral d theta pi of theta and then probability of the data given theta, right? And this expression we already know, right? Okay, so now let's see where does this lead us, okay? So this would lead us to, okay, so where do we do that? Let's do it here. So this, well, maybe I have still enough space here. Okay, so what does Neyman-Pearson is telling us? Neyman-Pearson tells us probability of data given H1 divided by probability of data given H0. Notice that I don't have a log here. The log was inserted with convenience. If it's not convenience, we will use something different, okay? So let's see where does this lead us. How much time do I have? So I have until 10:30, right? Good. To do. Okay, so you have integral, and I mean the constant will cancel again, so I don't need to know the determinant of C. And it's going to be e to the minus half, and then I will have a d minus t.
Barak, you can stay calm until 10:45, not until 10:30.
Okay, thank you. D minus t of theta. And underneath this thing, I'm going to have, so c minus 1, d minus t of theta again. And here I will have e to the minus half d c minus 1d. Okay? Now, again, what's going to happen to me, okay, is that the d is going to die.
Missing a pi next theta. So you're missing a pi.
Thank you. Okay, so this is not an integral, this is a scalar, so I can shove this in. By the way, if H0 had 3 parameters, maybe it wouldn't go in so easily, okay? So my advice to you, stop with the madness. Write Neyman-Pearson, start to end, derive it, okay? I've seen so many mistakes, you can't even imagine. Okay, so this is equal to, so now I have integral d theta pi of theta e to the, so now I'll have t in c minus 1d minus half t c minus 1t. And notice that this thing is also a function of theta. Okay, so now I will not be able to ditch this term so easily. Okay, so now you see what happens to the physicist. The physicist, if he doesn't know Neyman-Pearson, doesn't know the Maxwell equations, he just knows match filter. Okay, he just says, I know this formula, here is my test, and I'll just add a theta here, and you will make a mistake. That mistake, okay, that uncontrolled approximation, uncontrolled, I don't know, normalization, was in the original data analysis of LIGO 01 and cost them 30% sensitivity, 30% volume, I'm sorry. Okay, now imagine this. Okay, you built an interferometer for $1 billion. Okay. Okay, so we are not going to make this mistake. We are not going to ditch this. Here is an integral. Compute. Jonathan, you're my student. Compute. In general, it's not so easy. Okay, that's a 15-dimensional parameter space integral. And computing it for every point in time and for every whatever is not easy. Computing it once is not easy. Okay? And here comes the part where I told you that you have to be a good physicist, okay, or a good statistician. You need to use some approximation that on one hand is useful and on the other hand you can compute. Okay, there are few ways in which you can approximate this. It's an integral, and here there's some function. Okay, this function is e to this something. Okay, what is it? If I have if I plot now as a function of theta this integrand, okay, if I plot it now, so it looks something like that, and then there's something that shoots to the stars. Okay, so this is not to scale. Okay, this shoots way higher than I can plot. Okay, and how do you approximate this integral? Okay, so there's the stupid answer. The stupid answer is maximum. There's the better answer, which is the area of this Gaussian, which is the quadratic approximation. Okay, so what do we need? We need somehow the maximum and the width, and that would tell me the area, right? So in the end, it's going to be something like maximum over theta, okay, of pi. So here is an approximation. This approximation, you have to check if it's a good approximation, how much did you lose by this approximation? Some parameters you can use this approximation, some don't, okay? The example I give in my course is like in gravitational wave astronomy, there are the parameters in which you can use this, and there are parameters in which you cannot, okay? So let's see what are the actual requirements. So maximum over theta of pi of theta, and then e to the Tc minus 1 d minus half Tc minus 1 t. Now, if I remember, okay, and let's remember that t has a theta. If I remember, not only that t has a theta, if I remember that t has an amplitude, has a distance parameter, okay, which, you know, not in all models it's possible, but in this model it is possible, okay? Then I can specifically perform the maximization over the amplitude here, and it turns out that the maximization over the amplitude leads, okay, so maximum over amplitude okay. So, and you remember, I care about only the, so now that this is my test statistic, you remember this thing is going to be compared to some eta. So now that this is, I decided that this is my test statistic, I'm allowed to take a log, I'm allowed to do many things. So I will also take a log, okay? And what I will remain with is Tc minus 1d plus some log of pi of theta. Okay, so that's not going away. Okay, and I'll have some log term, which I'm not going to compute. Okay, I'll have some log term that, so this is something like d L d theta. So in general, it's some Fisher information, whatever. Okay, so there's some log terms of the width of this Gaussian. Okay, and that appears as another log term. Okay, so the physicist that knows only match filter will say this is their test statistic. The better physicist, the one that knows, adds these log terms. Now, does it matter? What are the effects that these things carry in their capacity? So, for example, suppose I have a pipeline, and my pipeline wants to detect both binary neutron stars and heavy black holes. So heavy black holes, if I look at my template, where is Javier? If I look at Javier's template bank, and I look at a black hole that is I don't know, between 20 and 30 solar masses. Okay, then I look at this bank, and even if I'm over exhaustive, there's like 100 waveforms. And I can tell you a secret. One of them had already detected more than 5 different gravitational waves. Okay, so the ones that are vanilla, spin 0, they detect gravitational waves like mad. Okay, and if I look at the 1 to 2 solar masses, so that's formally the neutron star black hole mass, then I'll have something like 10 to the 5 waveform. And the log term that depends on the theta, if you look what it is doing is some priorism, which, okay, the probability density for per log chirp mass is kind of the same. Okay, so this is a weak term. And here is a much stronger term, the width of the Gaussian. So the fact that here there are 10 to the 5 templates, it really means that if this is theta, then on that side of parameter space, the width is minute. And on that size of parameter space, the width is 3 orders of magnitude bigger. So that means that effectively, you need to have a different eta, okay, a different eta for the binary black holes and for the binary neutron stars. And these eta carry away information of like 3 orders of magnitude different phase space density. Okay, and that's the reason why you would see in the catalog, you would see binary black holes at SNR 8.5, but binary neutron stars 9+. Okay, actually even 9.5+. Okay, and that if you enforce it globally, if you close your eyes and enforce it globally, you'll have 9.5+ everywhere. Okay, and because this difference between 8.5 and 9.5 is 10%, you would lose 30% volume. Okay, one mistake, 30% volume. Okay, good. Okay, so now our spherical horse in a vacuum now is now a little bit elliptic, and it has already, I don't know, some legs. Still doesn't look much like a horse, but we will get there. Okay. Now we have some weird test statistics now. So now it's not exactly this Gaussian, it's not beautiful. And now you have these log terms, and who knows what this maximization have done. Okay, so now the test statistic doesn't actually look Gaussian. Okay, it's a fact of life. It doesn't look like a Gaussian. Even if the noise is Gaussian, it doesn't look Gaussian. Okay, so what do we do now? So first of all, we breathe. We remember that Nyman-Pearson had guaranteed us that we are doing the optimal thing, unless that approximation had failed us. We've made one approximation and we know exactly where it is. It's important. Okay. So unless that approximation had failed us, we are tied to the Nyman-Pearson. We are still standing on the floor. And we just need to figure out what is the new eta. Okay. Now, as von Neumann told us, you could be smart and compute, and you could be even smarter and just Monte Carlo. Okay. Because all these computations, they are kind of useless. It's all in order to compute some eta, right? So let's not get religious about this. One of my better teachers told me sometimes that what's the difference between integrating an ODE and applying a sine function? There is no difference. Anyway, I will use the computer to compute. Okay. So, we just need to compute what is this eta, and we don't care how we do it. And the best way is Monte Carlo. Okay. For this particular thing, the best way is Monte Carlo. So we have our test statistic. Okay. Sometimes it is called rho squared. Okay, but it's a notation. S, rho squared, bananas. Okay. So they call it rho squared for some obscure reason. And we have how many times it happened. And just in order for the plot not to exit the whiteboard, we will just write the log of how many times it happened. Okay. And now let's remember. So we have these 15 parameters. There's one of the parameters is the time. Okay. And we have 10 to the 7 seconds of data. And the autocorrelation function, like what is a time in which the waveform is already completely different, is like a millisecond. So there are like 10 to the 10 options. Okay. So but by this number, what I mean is that we make this maximization on little time segments. Okay. So max over theta. And t belongs to some t0 plus, I don't know, 1 millisecond. Okay. So now we have lots and lots of these things happening, and we can just plot how it looks like. And you notice that I'm plotting a straight line as much as I can plot a straight line, and that it does not start from 0. The reason why it doesn't start from 0 is that this maximization over 15-dimensional space, near 0, okay, so if you really look near 0, it's something like that. Okay, but far enough in the distribution, this is just going to decline exponentially. And there's a good reason for that. So first of all, if there was only one option and it was indeed a Gaussian, then it would indeed be this exponential, okay, because that thing is s squared, okay? Well, I'm allowed to apply any monotone transformation. I will square, why not? And it will be an exponential. And it's a particular exponential. It's e to the minus rho squared over 2. Okay? This exponential. Okay? And it turns out that if you maximize over lots and lots and lots and lots and lots of phase space, then the tail distribution is indeed going to be an exponential. And the normalization is going to be some feature of that integral. Okay, so it's a feature of this integral. But in the end, it's going to look like that. So this is the probability of rho squared given h0. Okay. And if you now Monte Carlo and compute what is the probability of this rho squared given h1, then you will find that it's some power law going like that. Okay. It actually diverges near 0, so it's a bad notation. It's a weird fact. No, it does not diverge near 0. It does like that. Because the maximization is going to kick in. Anyway. So this is this probability of rho squared given h1. And now that I run the pipeline, I process 10 to the 7 seconds of LIGO data. If I have an event and this event is here, okay, then I know what's the inference. What is this event? It's a random chunk. Okay, and what is this event? It's a log scale, and whatever. Um, and this event is the real deal. Okay. And it could be that this thing is 8, and this thing is 8.6. Okay. SNR. So this is 8 squared, and this is 8.6 squared, as written in the LIGO paper. Okay. This is the deep meaning of the fact that we talk about this SNR, because this thing is exponentially declining with the square of the SNR, and even minute changes change completely the inference, okay, because of this exponential. Okay? Good, so now you know how to read these papers. And let's talk about other things that they say. So for this event, they sometimes quote the integral. Okay, so it's a weird thing to denote, but they sometimes quote the integral below this continuation, okay? And they call it the false alarm rate, okay? And they say it in units of time so that you can interpret if this is something that happens once a year, once in 100 years, once in 1,000,000 years, or once a month, okay? So that thing would maybe have a once a month, and that thing maybe once in 100 years, okay? So that's the false alarm rate. And there is another thing that they quote, which is the P astro, okay? So P astro is just a little bit of Bayesian nonsense. And they would say the following thing. They would say, I'm saying nonsense, but it's actually a useful quantity. So they would say, here is a probability density of rho squared given h1. Here is a probability density of rho squared given h0. This probability density, let's not make it integrate to 1. Let's make it integrate to the actual rate. Okay? So I would multiply that thing by the amount of time I have. So this is actually already kind of in these units. And I just need to put here the rate of h1. Okay? So now this red thing doesn't have an actual scale-free thing. And again, we are making a decision, and the data in front of us is just rho squared. So how should we make the decision? Probability of rho squared given h1 divided by the probability density of rho squared given h0, right? Bigger or smaller than eta. Okay, so that's the decision. So that would tell you, let's say that you've done it with the rate, that would tell you where is this point, right? And now instead of this, okay, let's make this decision. Let's make the eta, okay? Let's make a Bayesian decision about this, okay? So probability of h1 or rate of h1, probability of h0, okay? What did I want to say? This is what I wanted to say. Prior of h1 divided by prior of h0, okay? So if I had this, I have this R as a meaningful thing, then this is what is written, what is denoted by this red line, okay? And you could say, if I know the ratio of pH1 divided by pH0, and I also know P of H1 plus P of H0 is equal to 1, right? And I can convert these two equations to an actual P of H1, okay? And this is what is sometimes called P astro. Okay, so 1 over 1 minus whatever this ratio. Okay, so this ratio is the information within, and you take this equation and you compute this P of H1.
The left-hand side is given rho squared, right?
probability of Weizmann given or square.
Thank you, Ariel. It's much harder on the board. Okay. You're not the only person having this feature, Bruce. Okay. So how much time do I have? That was exactly my plan for today, and I have 5 minutes. So let's talk about our horse. So now our horse is no longer this spider. Okay. So now it has some overall shape. Okay, maybe it also has a tail. Okay, so we have almost a horse, and maybe we can talk about how to arrive to this situation that we even have this maximum over theta for the entire bank. So that's like a practicality, okay? So here is a well-defined quantity, right? We are computing it and we can make statistics out of it. Okay, now let's talk about the practicality of how to even get there. So maximization over theta. How can we do that? Okay, so there's a continuous phase space eta, and it really has this feature that if I evaluate the likelihood of that eta, and that eta is wrong, it doesn't tell me anything about the fact that there's a huge, clear, correct solution over there. Okay, and in one-dimensional space, it looks nice, but actually it's 15-dimensional. Some of the parameters are not very effective of the signal, and some of them are very effective of the signal. And so there's like a frequency-like signals, which kind of look like this. And there are phases which kind of look like that. Okay, so if you have theta and you have this integrand, okay, so some parameters, let's say inclination, okay, they have features like that. Okay, there's no logs. Okay, so how do we proceed? Okay, so we say, let's prepare for the worst. Preparing for the worst means that we have to have a grid. And the width of this grid is going to somehow be represented by this width of how wide is this peak of the right solution. Okay, so let's write some math in order to exactly characterize this, and we don't need this anymore. So the function we are going to compute has two parts, the parts that has a theta and the parts that it's like the match filter. That thing changes very, very slowly with theta, okay? So this theta and the next theta, they have the same log terms, but that thing, tc minus 1d, e to the tc minus 1d, that thing is very wild, okay? So there's a phase space. Here is the phase space, okay, of all thetas. And what I want is somehow to have a grid in this phase space such that if an actual event happens with position, regardless where it is in this phase space, okay, I want to guarantee that I will find it. What do I mean by I find it? I mean that my optimization code, the one that calculated the maximum, started close enough to the maximum so that it actually reached the maximum. Okay? So somebody is going to compute t c minus 1 d, but this t is with that representative. Okay, so that's theta 0. Okay, and D has some particular theta. Okay, so now so this would be the test statistic S. Okay, and it will be normalized by square root T theta 0 C minus 1 T theta 0, right? Because this is the formula I'm going to compute. So let's see what actually is going to happen if I have the wrong template. So if I have the wrong template, then E of S is T theta 0, C minus 1, T theta. Okay, so this is what I'm going to have. What would have happened had I computed with the right template? Okay, so if I have computed, so this is S theta 0, S theta, okay, so the expected value of S theta is T theta C minus 1 T theta divided by the square root of T theta C minus 1 T theta. Okay, so E of S theta 0, so E of S theta 0 divided by E of S theta 1. And let's assume that these two things are equal, the denominator, okay? So that's going to be T theta 0 C minus 1 T divided by the square root of T theta. Actually, I don't need to assume that. Anyway, T theta 0 C minus 1 T theta 0 multiplied by in T theta C minus 1 T theta. Okay, so that is what people call the match. Okay, did I do it correctly? What have I done? No, I think it's right. Okay, so this is what people call the match. So it's just like that, and this thing is exactly square root upright, and when I divide, it's here. Okay, so this is what people call the match between waveforms. And that's a quantity that you would want your bank to guarantee. I want my bank to guarantee at least a 0.95 or 0.97 match. Okay, why? Because I'm very conservative and I built an instrument that's worth $1 billion. Okay. I think we will stop here, right? I'm already late. You should have told me. Okay, so I'll stop here and let's continue later with the more practicalities.